this unit, or this section of the unit, I should say, is biochemistry, and it will take us quite a while to go through the various sections of this. There's several labs that are related to biochemistry, and it sort of also starts to touch a little bit on genetics, as we talk about nucleic acids as one of the important organic molecules that's relevant to living things. So we sort of get to that, which relates to genetics. So it'll take us a little while to move through this whole section. But we're going to start off with just sort of basic review of chemistry that I know you guys have already had, and we talked about some of this back in 7th grade, but we'll talk about some other aspects and talk about some other concepts related to biochemistry. Yeah, Cormac? It's for 7th grade. So as we go through our section, it's really split first into introduction to some chemistry. Then we start to talk about various types of organic molecules. And we do that by first discussing carbohydrates, so these molecules, then moving on to lipids, from there going to proteins, and finally nucleic acids. So we'll talk about each of those broad categories that are important to living things. But we'll start with the basics of chemistry. So the atom, and this is all review. So we know that an atom is a sort of the building block of matter. It's a fundamental particle, I guess, that makes up the physical world. All matter is made of atoms. And an atom really is mostly empty space. So I remember the experiment that we talked about. There were various models of what an atom might be structured as through the years. And that model changed over time. So I remember, like, we talked about the plum pudding model, where you had a solid mass with little bits of electrons stuck in it like cookie dough. But we know now that atoms are basically mostly empty space. Does anyone remember the experiment that confirmed that? We modeled it using marbles.
Wasn't it like someone had a piece of gold and then they shot protons?
Yeah, that was the gold Rutherford, the Ernest Rutherford gold foil experiment, where he fired particles at a very thin layer of gold and saw that most of those particles did what? Passed right through it like there was nothing there. Every once in a while, one of those particles would be deflected, because that is a particle that actually struck the nucleus of the atom. But the vast majority of those particles went right through, confirming that most of an atom is actually empty space. But anyway, we have the nucleus, which is the very dense central core of an atom, which is composed of the protons and the neutrons. And then surrounding that nucleus are the electrons. So those particles are called subatomic particles, protons, electrons, and neutrons. We'll just kind of summarize them a little bit. So a proton found in the nucleus is a positively charged particle. Remember its mass? 1 atomic mass unit. Oh, sorry, we're going down. Neutrons have no charge to them. They're electrically neutral. And electrons have a negative charge. The mass of a proton, as you guys just said, is 1 AMU, atomic mass units. A neutron, also 1 AMU. And an electron, pretty much 0. It's not, technically it has some mass, but it's such a minuscule mass that it's basically irrelevant when we're talking about nuclear attack. So if you remember, when you look at the periodic table, you have various numbers, and I gave you a periodic table you can refer to. We're not going to need to use it a whole lot, but you have it there. And so when we look at a periodic table, by looking at the atomic mass and the atomic number, we can figure out number of protons, electrons, and neutrons. Okay? And so when we look at a periodic table entry, they're set up in lots of different ways. Your entries look different from this, but no matter what it looks like, you can figure out which numbers are which. The whole number is the atomic number. The decimal number is the atomic mass. You also have electron configurations on some periodic tables. So this is oxygen, atomic number 8, atomic mass 15.9994, electron configuration of 2 and 6. So how do we find the number of protons? Taylor? I'm sorry, Grace? Yeah, the atomic number. How about neutrons? How do we find the number of neutrons? Caleb?
You would like round the mass and then subtract it from.
Yeah, it's the atomic mass minus the atomic number. That's the reverse, sorry. Switch that. Atomic mass minus atomic. Yeah. And electrons? Sophia? There's also the atomic number. Okay? Because most atoms are neutral from the outset, and so the positive charge balances the negative charge, have equal numbers of protons and electrons. So we have some examples here, okay, of a carbon atom with 6 protons in the nucleus, 6 neutrons in the nucleus, and then 6 electrons around the nucleus. Oxygen, how many protons? 8. How many neutrons?
8.
Yep. And how many electrons? 8. All right. So why is the atomic mass not a whole number? So the atomic number is always a whole number, but why not the atomic mass? If it's protons plus neutrons, that should be a whole number, right, Corwin?
So electrons.
Nope. Doesn't have to do with electrons, because for electrons, what should that be? Higher than 16, right? But it's not, it's lower than 16. Grace?
Is like 1 and that rounded number is roughly?
No. Has to do something we've already talked about today.
Isotone?
Yes, because there are multiple isotopes of oxygen. Okay? Different versions of oxygen. They all have the same number of protons. All oxygen has 8 protons. But so looking at that then, what do you think some of the isotopes of oxygen are? Are they have more neutrons or less neutrons than the typical oxygen? Why less? Yeah, because the atomic mass is slightly less than 16, there must be some isotopes of oxygen that have 7 neutrons, and that brings the average down below 16. So this is an average mass of the atom. The electrons are found at different energy levels, or orbitals they're sometimes called. Okay? They fill up from the inside outward, from the closest orbitals to the nucleus to the outermost ones. Each level can only hold a maximum of a certain number of electrons, and that varies depending on what level it is. We sometimes draw them as these circles orbiting the nucleus. It's not really what they look like. It's much more complicated than that. They have complex shapes. The different orbitals have different shapes. You'll study that probably in chemistry next year. But what's important for our purposes are the outermost electrons. What do we call those? The valence electrons. Because the valence electrons, those electrons found in the outermost level, are what determine how that atom interacts with other atoms. So that's what's important. So again, we have the periodic table, which you have in front of you. It's organized a certain way. so that you have the various groups going vertically through the periodic table. Okay? And elements within a group have some similar characteristics, similar properties. They do have names that go along with them. You don't really, you know, this group over here, you know what they're called? Noble gases. Okay. We have metals and nonmetals in the periodic table, sort of a broad category. Metals generally are on the left side of the periodic table, and nonmetals on the right. And metals and nonmetals have different characteristics, different properties, and that is mainly due to the number of electrons in their outer shell. Metals have between 1 and 3 electrons in their outermost shell. Nonmetals have greater than 4 in their outermost shell. Most metals, when they interact with other compounds, will lend or give away electrons, because they're trying to get rid of those 1 or 2 or 3 in their outer shell so that they can eliminate it and get to a full shell that's beneath it. Most metals are solids, although mercury is a liquid, it's a metal. And they're good conductors. They have other properties as well, but we don't need to go through all those details. Nonmetals generally are trying to gain electrons to reach what number? 8. 8 is generally a full outer shell, which makes that atom stable. Most of the nonmetals are gases at room temperature and generally are poor conductors. Okay, we have some terms we need to know. Ion. So we said that most atoms, because they have balanced numbers of protons and electrons, what's their overall charge? And they're neutral. But sometimes an atom can gain or lose what? Does it gain or lose protons? No. It can gain or lose electrons. And so if an atom gains another electron, what happens to its charge? It goes from neutral to what?
Negative.
Right. And if it loses an electron, it goes from neutral to positive. We call those charged atoms an ion. When an atom gains or loses an electron, it then has a certain charge, a positive or negative charge. We call that an ion. There are also those we talked about back in 7th grade, the radicals, the polyatomic ions like nitrate, phosphate, hydroxide. Those also have a charge to them. For example, hydroxide is a negative charge. Nitrate is a negative charge. Phosphate has a negative charge. So if an atom gains or loses an electron, it has a charge, and we call it an ion. Valence electrons, those are the outermost electrons. Okay? So here we have an example of sodium. Okay? And sodium, if it loses an electron, okay, it becomes a sodium ion with a positive charge to it because it lost one of its electrons. Valence electrons are the outermost electrons, the electrons in the outermost shell. And these are the electrons that participate in chemical reactions, that interact with other atoms, that can be shared with 2 atoms or given away to another atom. When we're looking at those valence electrons, we can also determine an element's valence number, or sometimes called oxidation number. And this is how many electrons it needs to borrow or lend to get full, to get to 8. Metals are lenders of electrons. Nonmetals are borrowers. For example, calcium. Calcium has two valence electrons. Therefore, its oxidation number is +2. It has 2 extra electrons that it would love to get rid of, to give away. So it got rid of those 2 on the outer shell, and then the level underneath that would be full, and it would be stable. Chlorine has 7 electrons in its outermost shell, 7 valence electrons. So chlorine is looking to gain how many?
1.
Just 1. If it can gain 1, it will have 8. It will have a full outer shell, and it will be happy. So its oxidation number is -1. When metals and nonmetals join compounds, okay, then they can make each other happy. And the 2 chlorine atoms can get together with 1 calcium atom and form calcium chloride, a type of salt.
Is
Sophia?
this the basis of all chemical changes?
Not all chemical changes. These are sort of somewhat simplistic metal-nonmetal reactions. When you have a metal and nonmetal combining, they have a pretty simple reaction when they're going to share certain electrons. But as you see, there's much more complex reactions that go beyond this. But that's part of it. And they all do involve these outermost electrons. It's just a determinant of how they interact. Isotopes. Isotopes are atoms with different numbers of neutrons. Carbon has 6 protons. All carbon has 6 protons. If it had another number, it wouldn't be carbon anymore. But there are various versions of carbon, various isotopes that have different numbers of neutrons. There's carbon 12, carbon 13, carbon 14. When we have those numbers, what does this number represent? Not necessarily. It can become radioactive, but not all isotopes are radioactive. We call it a radioisotope if it's an isotope that is radioactive, that can decay, break down, and give off certain radiation. The number here is telling you the atomic mass of that isotope. So for example, carbon 14, how many neutrons does carbon 14 have? 8. Has 8. Because all carbon has 6 protons. Carbon 14 has 8 neutrons. Carbon 13 has 7. Carbon 12, 6. Which version of carbon is the most common? How do you know that? Yeah, its atomic mass, its average atomic mass is very, very close to 12. The vast majority of carbon on Earth is carbon 12. But there are some amounts of carbon 13, carbon 14 that bring that average up a little bit. Okay? There's different versions of hydrogen. Okay? Hydrogen with no neutrons. Hydrogen with 1 neutron or with 2 neutrons. It's all hydrogen, okay, but it's different isotopes. And finally, isomers. You're going to see, for example, you guys remember glucose back from cellular respiration. What's the chemical formula for glucose? Caleb?
C6H12O6.
Correct. Okay. That's sort of simplistic to say that. And that's what we taught you. But that glucose does have that empirical formula, but there are other compounds that have the exact same formula, but are not glucose, but are other compounds. They have the same formula, but different structure, and often have very different properties. So when we say glucose is C6H12O6, what does that mean? What do those letters and numbers mean? Grace?
6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen.
Correct. But how those atoms are arranged and connected with each other can vary widely. There's lots of ways you could connect 6 carbons and 12 oxygens and 6 hydrogens. And when you connect them in different ways, you have different isomers. So here's an example. This is butane. Okay. So how many carbons? How many hydrogens? 10. C4H10. But this is also C4H10. You counted up all the atoms, still C4H10, but it's in a different structure. Okay? It's an isomer of butane. This is called isobutane, and it has different properties from butane. All right, so when we talk about biochemistry, which is what we're currently studying, we're talking about the chemistry that's related to living organisms. Bio meaning living, and then chemistry. And when we look at the various compounds and elements and atoms that make up living organisms on Earth, there are really 4 main elements that make up all living things: carbon, hydrogen, oxygen, and nitrogen. Those form the vast majority of the mass of all living things. Three out of the 4 of those are gases at room temperature. They form diatomic molecules where you have 2 atoms of oxygen or hydrogen or nitrogen bound together. Okay? And together they're combined to form what we call organic compounds. So organic compounds, this is, it's not related to sort of agriculture or health. It's not like organic carrots that you buy at the store. That is a completely different use of the term. So you sort of have to ignore that. When we're talking chemistry, organic compounds are compounds that contain hydrogen and carbon. If a compound has both carbon and hydrogen, it is organic. Generally, these are made by living organisms, although there are some organic compounds that are formed by non-living processes. If hydrogen, they have carbon, then they have other atoms as well. We will talk about 4 main groups of organic compounds: carbohydrates, proteins, lipids, and nucleic acids. Now, if you have siblings in college, or you know relatives that are studying medicine or to be a pharmacist and so forth, you may have heard of organic chemistry. Does anyone have relatives that have taken organic chemistry? Okay, yeah. And you may hear horror stories about it. That's one of the most difficult courses that you take in college, because there are so many varieties of organic compounds that are formed. Organic chemistry often involves memorizing the various structures and the naming conventions, and can get quite complicated. We will not get that complicated. We're going to talk about these 4 main groups of organic compounds. Okay? Here are some examples of very simple groups of organic compounds. You have hydrocarbons. You have alcohols, aldehydes, acids, esters, ether, ketone, amines. All these various groups, which you would study each group and learn how to name these things, how to identify these molecules. That's what you would study in organic chemistry. Okay. But there are also, important to living things, are some inorganic compounds. Okay? And inorganic compounds, they may contain hydrogen, or they may contain carbon, but they don't contain both. Examples: water, carbon dioxide, sodium chloride, hydrochloric acid, sodium hydroxide. These are all inorganic compounds. So if we look at, what are the elements that compose a human? The ones we just named: carbon, oxygen, hydrogen, nitrogen. Those are about 96% of the composition of a human. then these other elements compose another 3.5%. Magnesium, chlorine, sodium, sulfur, potassium, phosphorus, calcium. And then the trace elements, of which there are small amounts in here. All right, let's finish up today by talking a little bit about bonding. So when atoms connect to form compounds, they do this by forming bonds between atoms. A bond is sort of an attractive force holding atoms together. And in the bonds of molecules, there is energy stored. Okay? When you break those bonds, the energy can then be extracted. And that's what our cells do. They extract energy from the bonds holding, for example, glucose together. These bonds involve the valence electrons. This is a topic we never got into in 7th grade. There are different types of bonds. We're going to talk about ionic bonds versus covalent bonds. And the names will give you some information. Ionic bonds. So what's an ion? A charged atom. So if I have two charged atoms, one that has a positive charge and one that has a negative charge, what do you think happens? No? How about, no? Positive and negative charge? How about the north and south end of a magnet?
They repel each other. Oh wait, they go together.
I think both.
They go together.
They merge.
They go together. There's an attractive force between a positive and negative charge, just like there's an attractive force between opposite poles in a magnet. How about the same poles? They repel. Okay? So ionic bonds are formed when there is a gain and loss of electrons in an atom, giving them a charge. So if we take a simple ionic compound, table salt, sodium chloride. We just talked about sodium earlier. Okay? If you look on your periodic table, how many valence electrons does sodium have? Has one valence electron. So what does it want to do with that electron? Get rid of it. How about chlorine? How many valence electrons? 7. What does it want? To gain one. So, if sodium were to give an electron to chlorine, sodium would have lost one electron, giving it what kind of charge? Giving it a positive charge. Chlorine has now gained an electron, giving it a negative charge. And we know positive and negative are attracted to each other. And so sodium, chlorine, and chloride form, table salt. Now, the sodium becomes positive, the chlorine becomes negative, and those ions are then attracted to each other. And they have vastly different properties than the original elements. I told you this in 9th grade, but sodium is a very dangerous reactive solid. Okay? Often sodium has to be kept in a layer of oil so that it doesn't react with oxygen on the air because it's so reactive.
What happened?
Yeah, it just reacts very violently. If you throw a piece of sodium in water, it reacts, it releases tons of energy, it gets really hot.
Wait a minute, don't we eat sodium?
No, not elemental sodium.
Oh, okay.
So chlorine, noxious gas, poisonous, used in mustard gas. Okay? And it's poisonous. It can damage your lungs and kill you. But again, this explosive metal and this poisonous gas, when combined, form table salt, something we use every day. The properties of a compound can be vastly different than the properties of the individual components. So this is an ionic bond.
I was thinking sodium was salt.
Yeah, no, sodium chloride.
Yeah.
All right, finally, let's use our last bond. So covalent bonds. Can you imagine what this means? Covalent. when atoms don't give away an electron, but share an electron. So as an example, let's look at methane, CH4. So methane is made of a carbon atom. If you look on your periodic table, carbon has how many valence electrons? 4. So what does it need? 4. It needs 4 more to get to 8. Hydrogen, how many? 1. Okay. But that first energy level to be full, you know what the number it needs? Doesn't hold 8. It holds 2 only. So if we have 4 hydrogen atoms, each share an electron with the carbon atom, and these electrons are sort of held in common, how many does carbon end up with? Total shared electrons. 8. How many does each hydrogen atom end up with? 2. They're all full, they're all happy, they're all tightly bonded together, forming methane, CH4. Okay, carbon dioxide, same idea. Carbon has 4 outer electrons, 4 valence electrons. Oxygen has how many? 6. Okay? So again, if we have 2 oxygen atoms share electrons with 1 carbon atom, the carbon ends up with 8. The oxygen atoms each end up with? Nope.
Oh, wait, no.
Also 8. And they're bonded together. Hold on one sec. Let's finish this last. So we can indicate a compound in different ways by showing its molecular formula, or being a little more specific and showing how those atoms are connected in its structural formula, or as we were just showing with an electron dot diagram, which shows how those electrons are shared between various atoms.
What was the weird dot thing that was?
Yeah, that's the electron dot diagram. All right. Talk about multiple bonds tomorrow. And we'll go over here.
You mean Thursday? Tomorrow we have school.
Yeah, Thursday.
No school tomorrow.
Boo.
Why don't you
Did you just say boo?
Yeah, because it's a day I don't get to see my students.